universe began, light has remained unchanged. Now, man has created a new kind of light with powers and properties unlike anything that existed before. Laser light.
Yo, hey everyone, welcome back to 0x2C podcast. And I'm Ryan again, and with my co-host John. And I hope everyone's having a good Sunday. How's your Sunday going, John?
It's going all right. It's going all right. I mean, just a lot of stuff on my end, but I'm really looking forward. I'm always looking forward to any 0x2C podcast related stuff and being able to once again stay true to our mission. And I'll just go first this time.
All right, let's do it.
All right. So for you, I know historically I've done, I think in the past two podcasts, I've done a lot of astronomy related stuff. And I think I went super abstract with talking about alpha and the fine structure constant. But this time I wanted to kind of bring things down to earth. Get it? Because I've been talking so much about astronomy. And I have an article for you about a recent development. It comes from phys.org. It's from Radboud University. And in 2013, so this is kind of old news, but there's been a lot of new developments with this tech. So it was discovered in 2013, and they found something called PIC gel, or the full name, or the full chemical name is polyisocyanopeptide. That's like a mouthful, so we just call it PIC, P-I-C. And it behaves a lot like the stuff that surrounds the cells in our body. And the kind of unusual property it has is that when you heat it up, it turns into a gel. But when you let it cool down, it becomes a liquid again. Now, this sounds kind of boring, but the really exciting stuff is what you can what you can use it for in a medical context. So what they found is that it's incredibly useful for cell cultures outside of the human body, and modifying properties of the gel can actually tune cell growth. And one of the major applications they're flaunting right now from their latest research is the growth of organoids. And for those of you that don't know what an organoid is, it's literally what you think it is. It's like a mini human organ that's grown from a test tube. So it has the same, like if I were to take part of your liver cells and I could make an organoid, it's like a little, it won't look exactly like a liver, I imagine, but the complexity and the structure should mirror in some sense your unique kind of, layout of your liver. So
okay. A question, John.
Yeah.
So organoid, is that something I've seen? I remember on like these TEDx talks, they would 3D print an organ with from those tissues from the cells.
I don't know about 3D printing, but it is in the same line of tech. Like sort of growing organs outside of the human body.
Gotcha.
Because I mean, like, have you ever played like the Halo video game series?
I never really went into Halo, but I did watch my friends play all the time. I was more of a Call of Duty diehard fan. Halo had too many lives, and I was like, this person's never gonna die.
Well, the only version of Halo I've ever played was Halo CE, Combat Evolved, because back then I had like a Windows 7 laptop, and I could run it on my PC. But I never in my life have I had any other console besides like the Nintendo Wii, which is pretty much like useless these days. But in the lore, or like because I've read a lot about like sort of the backstory to Halo, they talk about how in the future they have that technology like flash organ printing. So if you get wounded in battle, they can like yo, this guy needs a new heart, like now, let's go. So you like press a button and they just. So when I hear about this gel, that's what I think. Like I'm thinking like, dude, like imagine having a vat of gel and like, okay, well just wait like 20 minutes and you have like a new heart. That would be nuts.
Okay, wait, but what's the name of the gel again? It was start with a P.
It's called PIC. P-I-C.
Okay.
I'll go ahead and you actually just reminded me. I should drop the URL here in chat for any of our anybody who comes in that is interested in this stuff. And besides that, though, they're also interested in the context of stem cells. So stem cells are a special kind of cell you can find in the human body. They're incredibly useful because they stay in this kind of undifferentiated state. But later on in their life, if your body needs to heal certain parts, it can differentiate. So a stem cell could become a red blood cell, or maybe a skin cell, or a piece of muscle. Stem cells can do that. And there's a theory going around that stem cells, for certain treatments, injecting stem cells into the body the stem cell doesn't actually do the work. The stem cell gives off a chemical that triggers your body to then continue the healing process. So what these researchers are saying is that using this gel, they can get the actual chemical from those stem cells instead of having to inject those stem cells like in your body. So this gel has like a number of interesting properties that can control cell growth.
Oh, interesting. So with stem cells, I know this popular person, Joe Rogan. I know, I don't know him, but like I watch him, and I know he uses stem cells for recuperating. And what was I gonna go with this? But isn't that sort of isn't stem cells also like sort of they're trying to develop some new things with stem cells and like how they sort of heal your body's like different parts of your body?
Oh yeah, absolutely. Stem cells are, they've been in development for quite a while now, but it's still very new territory. I think we're just beginning to understand the mechanism behind how stem cells like differentiate, because we know they can turn into all these different cells, but the exact mechanism is kind of elusive. We're not too, at least I think we're not too certain. I haven't, stem cell therapy isn't my main.
Right. So instead of injecting it, you said this is gel. You don't have to inject it, right? Is that what?
Right. Well, there's a theory that says the stem cells aren't the ones that are actually like doing the work. They secrete a chemical, and then your body, like that chemical triggers your body to do repair work. So what they're saying is instead of having to dunk all these stem cells into your body, we can just get the secretion out and then use that as kind of like the therapeutic component, from what I was able to tell.
Okay, wow. Oh, wow.
I still like that video game, and like that kind of stuff is almost like the stuff of science fiction. Like you lose a limb or you suffer a major injury, and we can just regrow it. Like how like you grow a plant, you just pour some water in, and it just like to imagine that's within our lifespan. It's amazing.
Yeah, I mean, I'm just imagining, how people have succulents in front of their house? Because I have a neighbor of mine, they have like a bunch of succulents. Imagine just a bunch of just livers, or like people growing like
I mean, in real
body
like
parts. That would be insane.
Like cancer research labs, they probably, like I mentioned the organoids, right? So there probably is a lab somewhere in the world where they just like, oh, here's that little mini liver I've been growing for a week or so. I guess it's ready for testing now.
Now, do you know how long it takes to grow these?
I don't know. I imagine not too long, but I mean, it still takes some time.
Yeah.
But if you're interested, I mean, I'd encourage you to check out like organoids. That's definitely been an incredibly useful tool for cancer-related research.
Yeah, and I'm also interested. I hear about T cells. I think do you know? Have you heard of those before? T cells.
I think T cells are related to the immune system. Whenever you hear like,
that's right.
so maybe like immunotherapy, something that's like. But T cells are. I know way less about T cells than I do about stem cells.
Okay, because I'm thinking. Okay, no, I don't think it's called T cells. I think there's a certain. It's about extending sort of your life, but they target a certain. I forget the name, but there's much of research. I remember when I was studying biology, AP Bio in high school, they're learning how to extend this certain, I guess, cell that I forgot the name of, but basically it's supposed to extend your youth, or it's supposed to extend your life, but I forgot the name. But I know there's like a whole bunch of research going to that, especially now. I mean, I feel like people want to live longer. They want to look better. Look when they're 50, they want to look like they're 20.
Oh yeah, absolutely. That's always been something that it's been heavily pursued throughout history. Yeah, I think you remind me. There's been research as well into why certain animals, like I think lobsters don't like die of old age.
What? No.
Yeah, they don't die. I'm pretty certain it was lobsters, because they'll die of illness, or if you like, of course, if you like fry them for food, of course they're gonna die. But in terms of age, like if you give them a perfect environment where they're not bothered at all, and they don't die. I mean,
Wow, I did not know that.
Yeah. That is some, there's also like something called a hydra. They don't die. They manage to I think like continuously regenerate. That might be the wrong term, but I'm aware that they don't.
That's
they don't
very
die.
interesting. 'Cause
Yeah.
that's weird. I mean,
Yeah,
honestly,
definitely.
sea life, they live like I feel like it's such a different. It's obviously a different world, you know. Thinking about squids and how they survive underneath high pressures, like if they're able to be underneath. Have you seen those colossal squids on YouTube?
Yeah, I have. I definitely have.
I mean, to think that they're like 60 meters long. I mean, that's insane. And like,
Oh yeah, I think you might be talking about. There's another property called deep sea gigantism, and scientists still don't know why. It's like, why is it that the further down you go in the ocean, like why is it that animals get bigger? And we still there are a number of theories, but there's no like confirmed mechanism for why.
I wonder if it has anything to do with like pressure. Like, if the larger your body is, the better it is to, I don't know, to like handle pressure. Like this, I don't know. I'm just
That might be
assuming.
part of it.
Yeah.
They, one of the theories is like, okay, the pressure does like, it has some kind of a contributory mechanism. But once again, I'm not. The only reason I know this is because there's a YouTube channel. I think it's called like Deep Sea Oddities.
Okay.
And they do a really awesome job showing you all the freaky stuff there is, like in the depths of the ocean.
Right, yeah, and those things always freak me out. But I mean, that's interesting. We can't even go down that deep. That's like the other crazy part is that as much as we want, well, I don't know if people want to visit deep depths like of the oceans, we can't. Like we like right now our technology, we can't go that freaking deep.
I mean, we can. Like, I think it's part of it is like funding, right? Like, if you
That's
send
true.
an expedition down, like the problem with science is unless you can guarantee that the result of your experiment has an immediately valuable, a utility to it, there aren't that many people willing to fund it, right? Like, it's why we build those particle accelerators in Europe, and some people are like, oh, you could have, like all you're doing is like smashing, like how will knowing what
That's
the
funny.
fundamental particles of the universe be? Like, how will that cure cancer? How will that,
That's true.
reduce hunger, across the world? Yeah.
No, that's very true. Actually, it reminds me of I was reading into the new vaccine that just came out, mRNA, and apparently the person that was like die hard studying this, she, I forgot her name, but oh man, I should have noted it, but she couldn't get funding for her like research into mRNA, so they did an article about her. I forgot the name, but you can probably Google this. But yeah, it's the same issue is that if you can't get any funding, you can't do your research. And I think that's
Right.
like, that's the big, like, like pitfall of like a lot of research. And I'm surprised, yeah, the whole particle accelerator and what you brought up, like how they convinced the government and organizations to fund them.
Yeah, it amazes me as well. I mean, that was not a cheap project. CERN was definitely not cheap. I mean, this thing like crosses, I think, the border between two European nations, and it has produced very interesting results. But of course, to you and I, like to average people, we're like, so what if this particle is made up of, that's not going to affect me. Whereas so it's sort of the same thing with this deep sea exploration, right? Like you're like, whoa, like we found a new species of squid, and the people are like, well, you can't eat it and you can't make medicine out of it, and there's no immediate value. Whereas for medicine, right? Like the field of medical research. I mean, we want to find cures for diseases that may not have been curable before, or life extension. I mean, that's probably why this gel might, I think this gel has a good chance of being heavily funded in the future. But you make an excellent point, though, that it's just like we're as humans, we're much better at funding things that we think are, immediately applicable or useful to us. But in the long term, we're not really suited for that kind of stuff.
Yeah, and I was gonna go. So this gel, how does it happen again? How does it form that tissue, or like how does it grow again?
What do you mean, like the stem cells? How does it affect the stem cells, or?
Yeah. So like, how would you, like if you were to use this gel, how would you use it to make?
Oh, I see what you mean. So the focus of the gel is like growing cells outside the human body, right? So I take the cells out of you, and there needs to be a way to control the environment that your cells are growing in. So this gel can help kind of fine tune the settings required to control these cells. Because traditionally, I think for organoids, they used to use tumor extract. But the problem with using that extract is that it's really unpredictable. Like one extract is not the same as another, which is terrible for science, because one of the key pillars of science is repeatability, right? Like what if I told you, Ryan, like I did an experiment and I found out that 1 + 1 = 3. And then you'd be like, no way. If this is true, then if I do it, it should have the same result, right? But then you find out, like, wait, 1 + 1 = 2. So then you know that I'm lying. Like maybe there was a mistake in my experiment, or maybe even worse, I have some malicious intent. But yeah, so using that tumor extract, I might have a great success growing cells in one day, and then the next day it's like nothing happens. It's that's what I think is the problem with the tumor extract. So.
Oh, I see. So it sort of creates them. It's basically just it's a nice environment for these stem cells to be in order to cultivate what you need.
Right. You have a lot of control, way more control over the settings, and you can, as well as like the cell behavior. So.
Oh, okay. I see. Wow. So this article, it's sort of going to combine two articles because they're so related, and it's recent news. Has came out about the recently on YouTube. I was watching that they're basically, what are they doing again? I always have a brain fart.
What do you mean? What are they doing? This is the article.
It's like I'm talking to myself, and then I'm like, wait a minute, and then I'm like, okay, now I remember. But basically, yeah, they're just coming out with the mRNA vaccination. So they're supplying it to a bunch of these, I guess. Hospitals to give out to everyone, and and in this article, I think there's always been a question like, okay, this is a new vaccination, what's in it, right? Sort of, and there's a lot of people that are scared that it's a new vaccination. What are the ingredients in this vaccination? So recently in this article, it literally is what are the ingredients of the Pfizer COVID-19 vaccine, and so I thought this was interesting because I personally never really looked into what goes into a vaccine. I sort of, I don't think that's like personally, I was like, oh, I wonder what makes up vaccines, because I guess I never was really into that until now. I was like, oh, okay, it's cool to know what makes up a vaccine. And actually, John, do you know any like ingredients that you think would go into vaccinations, or do you already know that list?
I don't know the specifics of the mRNA one, but I know traditionally it's always been like they take an attenuated, I think attenuated is the official medical term, but in layman's terms, a weakened version of the virus. So your immune system kind of it's easier for the immune system to fight it off, and then your immune system learns like, okay, the next time I see this, now I know how to kind of get rid of this foreign invader and keep the body safe. That's like the really high level explanation. That's all I know.
Yeah, no, that's right. So traditional vaccines, they need to basically grow the virus in what they use now is chicken eggs. So they'll grow like a lot of viruses on these chicken eggs, which is surprising because I didn't even know they use chicken eggs to grow like these viruses.
Hey, it looks like Scotty said hi to us.
Oh, hey Scotty, thank you for stopping by. Appreciate it.
But keep going. So you mentioned that we used to use egg yolks or like eggs.
We still do. So a lot of clinics, laboratories, they'll use chicken eggs in order to grow the virus. But I'll go into more into that in a little bit. So let me give, a little history on what since when COVID has hit. So the first human case that was reported was to two officials was in Wuhan City, China, in December 2019. So just last year, right? And so many of the initial what's up?
Hold up, December 20. Whoa, that means like we're almost in a full year of COVID now because it's December right now.
Right.
Oh man.
Right. And it's crazy, you know, we've been, I mean, stuck inside pretty much, or like things have been shut down for almost a year now. And
Yeah. Oh my goodness.
it's sort of crazy to think about, you know, what impacts that will have on I guess future, you know, and anything like in market to finance to what will this bring? But
Right. Right.
yeah, but let's continue. So
Yeah. Definitely.
so the full genetic sequence of this virus was shared publicly on January 11th. And 12th, they gave like an approximation date. But since then, the sequence has shown to have an ecological origin in bat populations. So this is like where that meme came out, where like, you know, they were eating,
Don't eat the bats, or you'll get
right. And so this came from the. Let me make sure. I think I'll give the works cited after, but so I guess let me give some context of maybe people don't know what mRNA is. So mRNA is it's basically a single-stranded molecule of RNA, and it has a genetic sequence of a gene that is read by a ribosome in order to synthesize a protein that can be, you know, used in our body. And so it's basically, you know, like a strip of instructions that what we call a ribosome, which encodes this like instruction.
right. Like the ribosome helps build the proteins, right?
Correct.
Okay.
Yeah.
So that's sort of like the little factories of the cell.
Exactly. Yeah. And I remember in AP Bio, I would have to memorize like all this stuff from like the process of when the DNA sequence comes out of the nucleus to like where it gets transferred to the Golgi apparatus, sent out to like the
leading and lagging strand.
Oh
and like, okay,
gosh, don't no.
the tRNA and mRNA that's all floating around in the cell. And, oh man.
Yeah.
I don't think I would have made it far in biology. I think engineering is kind of like.
Yeah, man, it's a lot of memorizing. I'd say in biology it's all you got to memorize this, that, you know, this process.
Yeah, but I mean, you got to imagine like that's over billions of years of evolution. You know, like to imagine that you know, I guess for you know, for people of religious faith, you know, they would say that there is a divine force, a creator, which came up with this process, right? But you know, for the majority, I think of scientists who may not have or follow a certain faith, I think it's astounding to think that just over these many millions of years, this process could spontaneously kind of arise over time. You know,
right.
All these intricate mechanisms. Yeah.
And the thing about that is also now that we're able to sort of understand what's happening at that low level, we're able to use this technology in our vaccines, like the mRNA vaccine that came out with Pfizer and Moderna. So it's like, I mean, it's amazing to like what that research went into. Now we're seeing it being applied in our vaccinations, right?
Wait, so just to make sure, the mRNA goes to the ribosome, right?
So the mRNA, it basically it comes out of the nucleus. I'm 95% sure, but it's basically it sits into the cytoplasm. And then ribosome comes to it, and then it decodes the sequence. I could be wrong, so chat, make sure my AP Bio isn't tripping me on that one.
I'm pretty sure, like, you're right that it comes from but I think when it goes to the ribosome, then it has the instructions like, okay, here's the like generate this protein using the or is that another R? Oh, I feel embarrassed now.
No, that's okay.
To be fair, okay, for anyone in chat or anyone watching. When was the last time? It was like, what, 4 years ago you had bio?
Yeah.
It's been years, right? It's been years, okay.
give us a break.
Yeah, give us
But I mean, just, high level, the mRNA gets translated, what we call translation by the ribosome, in order to create these proteins. And specific proteins, in this case, like the spike protein, founded on the COVID surface. Okay, so now...
You're right. Sorry, I had to look at it because it was bugging me too. I just checked it. It does come out of the nucleus, and then once it hits the cytoplasm, it's up to like the other organelles to figure out how to produce proteins.
Great.
But keep going.
Let's go.
Yeah.
Okay. So now so we sort of explained mRNA and vaccinations. So like I was saying, so traditionally, the typical procedure in creating like traditional vaccines is that you put a weakened or inactive germ into our bodies, and then it teaches our cells how to make the protein, and it triggers the immune response inside our bodies to produce the antibodies to get the virus away, right? To prevent us from I guess from receiving the virus.
Getting sick because I mean you've already received the virus already. That's the whole. So the next time, it's almost like when you study, like you take a practice exam first, and then you take the real exam, and you're like, oh, this is easy. I know how to do this. That's exactly what we're doing to the human body. When we give it a vaccine, like, okay, here the immune system. Here's your practice exam. The immune system aces it, and then when the real virus or a foreign body comes in, it's like, I got this under control.
Right. And so I guess to compare mRNA creation versus the traditional vaccine, and when they're making it, is that traditional vaccines will take longer because it takes a long time to grow large amounts of the virus, which
you got to incubate it, right?
Yes, and they incubate it using chicken eggs, is what I read online. And fact check me on that one, but it sounded wild to me. Maybe, but when I read it, it said chicken eggs. I was like, oh, that's really cool. Things I eat in the morning are being used to cultivate viruses. So now let's go into the nitty-gritty mRNA vaccinations. So first, scientists thought that if we develop the exact structure of the mRNA that made the virus proteins, then we can just inject that sequence into our immune system to allow our body to get that exposure. So rather than injecting like a dead virus or I guess weakened form viruses. Now, if we just have that gene sequence and we trick our immune system to create the proteins, then we're able to. The immune system automatically will let's make our antibodies to defeat it. So this takes away from the process of having to incubate viruses, because now we're really just making it in our own. I guess selves in our own.
We use the body as the incubator, but we can. I would assume that using the mRNA method, we're not creating like a super virulent, like it's already like the moment the body sees it, it kind of knows like, okay, like right now, like we're gonna develop kind of the necessary countermeasures.
Yeah, and exactly, and that's another thing I should note is that we're not like. We're not infecting ourselves. This gene sequence that we insert is not going to harm us in any way. They made that very clear in the articles I was reading, because a lot of people like to twist it and say that, okay, well, why are you injecting the virus in yourself? Those anti-vaxxers, they're like, that's terrible. But yeah.
Right. I mean, they always come up with some kind of way to blow things out of proportion. They just say terrible things about the vaccine in an effort to deter people from taking it, which actually does way more harm than they think. So,
right.
Wow, it's really cool knowing how the mRNA thing works, because I think like before your explanation, I mean, I knew from the headlines, like, okay, mRNA is somehow helping us make this vaccine come out faster, because traditionally it takes a very long period of time to develop and distribute these vaccines. And vaccine development isn't always as straightforward as we think it is. Like, I think the headlines, I told you about this a couple days ago in Australia. They tried to administer Australia's version of this vaccine, and it ended up having the crazy, this unfortunate side effect that people who took HIV tests after taking the vaccine would test HIV positive, even though they did not have HIV. They had and for some reason the vaccine somehow had this kind of it is giving this false trigger to the HIV test. I think Australia has canceled or at least decided to postpone development of their version of the vaccine, because as you know, like different nations across the globe are developing their own kind of version. I think the UAE, United Arab Emirates or Emiratis, they developed their version. The UK had theirs, and we have the sort of Pfizer version. But they should all be highly effective. Russia has their own, Sputnik 5, although that's mired in some controversy. But
yeah, so that's interesting. I wonder if they're using the same procedure, and like I'm assuming they are, But
I think it's all mRNA, but maybe like within the company or within the country, maybe they have some different specifications here and there.
okay, yeah, then I should. That would be very interesting, like just look into like what Russia's doing, or. But yeah, I think hopefully, I mean, I would assume they're the same. I don't know,
Yeah,
but the company is what's different. I think that's
right.
Yeah.
They should have. I remember seeing this in the news as well. It was about how the Russian version of the vaccine, it's called Sputnik 5. A lot of people were a little upset because someone in the government, or I think it was a health official, they said, okay, when you take the vaccine, you cannot consume alcohol for 2 months.
Oh wow.
And in Russia's history, there's been there's a very high rate of like people there are particularly fond of alcohol. So even now there are protests like saying like, whoa, that's not reasonable. You can't expect, they thought it was not welcome news is what I mean to say. But that's the controversy around the Russian Sputnik 5 vaccine.
And I think since Russia's so cold, I heard when you drink alcohol, it actually will help you stay warm. Or is that a myth?
I
For
think
alcohol
it gives you
consumption.
that warm feeling, but it's not a sustainable thing to do. I think
That's true.
Eventually there's like some kind of detrimental. I don't know what the immediate detrimental effect is, but I know it just it's a temporary fix. Yeah, but alcohol has been like it's sort of like a major part of like the stereotype with Russia at the very least.
Vodka, right?
Yeah.
But yeah, so I guess I also looked up the process of these mRNA vaccines. And so basically, they first learn how to modify the mRNA so it doesn't damage our immune system and produce harmful reactions, because a lot of times, I guess in vaccinations, you're worried about how your body will react to it, right? Because it's an unknown substance that you're injecting into your body, and a lot of times this can create inflammation or things in the future that might occur. Like people have heard from autism has. In traditional vaccines, like I think the flu vaccine, they said that it had this certain. Let me make sure it's a name, but basically this ingredient of the flu vaccine contained mercury, and they said that it was somehow connected to autism, but
although that's now been like heavily debunked. Like the guy's has his credentials revoked, and it's total. The mercury part, I think, is still true. Like vaccines do contain, but I think the reasoning behind that ingredient is, first of all, the amount of mercury is incredibly small.
Mm-hmm.
It's pretty much near non-existent. But I think it was to help your cells absorb some kind of material. Like it does have a purpose. Doctors don't put mercury in vaccines to intentionally harm people. That's like one of the most ridiculous things I've ever heard. But it is there in incredibly like non-harmful amounts, and it's there for a very good reason. Yeah.
Yeah, and you took it away. That was exactly what I was about to go into. Is that that the mercury is a very small trace amount, so it won't won't kill you. It won't.
You will not get mercury poisoning.
Yeah.
And,
Yeah.
Yeah, it's like the amount of vaccine you would have to take to get mercury poisoning is like insane. Like I don't think I know the exact number, but I'm pretty sure like at that point there's probably like more vaccine than there is blood in your body, or like human volume. And at that point it's just you might as well just drink a tube of mercury if you really want to, instead of trying to get multiple vaccines, which is pretty ridiculous.
So after that, once we find out that how do we not damage our immune system, we make the mRNA pass through the immune system in a way, and how we do that is we coax these cells and we sort of we trick the immune system to accept it. Is really the key takeaway with these mRNA with the mRNA vaccination, is tricking our body into taking it. So I guess, yeah. So what does the mRNA vaccine sort of, I guess, do inside of us, basically? I sort of had this in my note. I don't know what I was typing. But the mRNA will allow us to well, the mRNA gives the instructions for our cells to make a harmless piece of the spike protein, like I was talking about earlier. And so the spike protein, I think it's very, if you guys have seen pictures of it on the internet, it's like these little spikes on the outside surface of the COVID. A lot of drawings draw it out. And once this protein is made, the cell just then destroys the instruction. Antibodies then realize, okay, there's something wrong. And then our immune system is able to attack it and create the antibodies to fight it off, which I find is very, the one thing amazing about our bodies is the way it fights off these viruses and like things harmful to from the outside that enter our body, and how we have like sort of these helper T cells and white blood cells that attack, the virus and eliminate it. It's such an awesome security measure for our own, for
the
evolution.
Human immune system, is a phenomenal, like one of the most amazing pieces of engineering in terms of biology. I mean, for those of you that are interested, there's a YouTube channel called Kurzgesagt. It's a German name, but you can look up. It's called like In a Nutshell, and they have I think 1 or 2 videos that actually explain like a huge chunk of the biological pathways. And the immune system has like all these cells that are just lined up, like they're monitoring your body, and the moment they detect that something's wrong, the immune system's ready to kind of jump into action and do its best to pummel that foreign invader out of your body. And it's interesting you mentioned that spike protein, because I've actually seen there's a simulation floating around that shows how that spike protein can literally, like, you have the sort of lipid cell layer, of a normal human cells, and the spike literally like burrows its way in, and it does this twisting motion. And this is on a molecular level. Like it twists and it kind of tears the cell wall open. And then, that's how the virus can inject its DNA into the...
gosh.
It's amazing. If you look up the spike protein, and that spike protein has been the subject of intense analysis, not just for biologists, but for chemists and people who focus on sort of molecular simulations as well. And I'm saying this from almost firsthand experience. I have a colleague of mine who has been using quantum computers to potentially, maybe find some kind of molecular compound or study the behavior of that particular spike. Yeah.
So it sort of corkscrews its way into there and then ruptures the cell. See, that's so crazy.
The goal is to open the cell wall so that the DNA can go in, and then that's like once the virus's DNA is in your body, that's how it hijacks your how your cell would normally maintain itself.
1 second, John. Quick shout out to Bro Man from the 5th floor. Thank you for the follow. Much appreciated. Thank you for the support. But yeah, I was gonna go into virus, because not all viruses are active all the time. So I remember in AP Bio we would talk about the dormant viruses. So they would inject and then they would lay dormant, until there's a certain factor that triggers it, and then it starts replicating. And there's different viruses that will live in the cell, or it's going to rupture the cell.
Right, because they make so many copies of themselves to the point where the host cell is driven to the point of starvation or exhaustion. It just bursts. Like if you look at it under a microscope, it's crazy. It's absolutely insane. Yeah,
and if I remember correctly from maybe Bao, it's the lysosomic cycle. Wait, right? There's a lysosomic cycle, and then there's which is the one where it breaks the cell open, and then the other one is I forgot. So.
Well, I mean,
I forgot.
It's been 4 or 5 years since we had biology. So.
Yeah, and I remember it was so interesting though, because out of AP Bio, what I learned the most was viruses, and just how cool they were, and the way that they hijacked, our good-looking cells to do their deeds, and they can't live on themselves. So, it's sort of like parasites in the way that they just leech on it, and then they'll duplicate without you even knowing it, and it's just it's amazing, just these things live among us.
Right.
But are they even living? They're just
That's an excellent point.
Yeah. Are they even alive?
Like viruses straddle, like viruses are part of that huge debate. Like, what is life? What do we consider as life? And for the large majority of the scientific body believes viruses are not living things. They don't fit one of the criteria. And there's like a sort of rough list out there, but it does challenge our definition, because it looks like it is living. I mean, it can self-replicate. It can Or well, no, it can't self. It needs a host cell to replicate. But it really. Oh wow. Okay, so let's see. Reanimated Nat. Thank you so much for that contribution. It's sort of like one of the things that Ryan and I love to see here on the ZeroX2C podcast.
Yes, fact checkers.
Fact checking, but also being able to learn something new.
Yeah,
this is sort of
that too.
A two-way thing. Like, Ryan and I are both rusty in our biology, so it's really nice being able to learn something in return as well.
Yeah.
So thank you very much.
Yeah. And I mean, because you got to think about it. Do these viruses have the plan of like, okay, I'm gonna die soon. I need to go find a host cell in order to replicate, because that's my life's goal. That's my, it's sort of it goes against the analogy of like, does a caterpillar know it's gonna become a butterfly? And I think I personally don't think it does.
Well, I think Ryan and I had a debate about this outside the podcast, and I gave a very kind of mechanical argument, right? I'm like, well, first you got to define what it means to know, but I think the real reason, like the real line of logic here, is what happens is that it's a natural sort of biological process, right? Like it just happens. I don't think they're very comfortable with it because biologically, they've done this a million times over throughout. Multiple generations of caterpillar or butterfly, but it's not something like they have to think about. Like they just. Well, but then again, you brought up that I forgot what the name of the test was to test if something is like conscious or. Yeah,
it's a very debatable test, but it's the self-reflection test. It's I think that's how if you Googled it, search up self-reflection test. It's basically a psychological test where they'll mark. And like with a marker on, like, say, an elephant's forehead, and have a big mirror in front of it. And if the elephant reaches for the mark and touches his own forehead, then there's sort of an argument that it's self-aware, that it knows that it's looking at itself through the mirror. Or the other way is the other option is if the animal or the object, the thing that's being tested is going to touch the mirror. And it doesn't know that it's like looking at itself. So like, if let's see those like dog videos where you hold a mirror in front of them and the dog will go crazy, or the cat videos, So there's an interesting fact is that babies, they aren't they with this test, they aren't self-aware. At least it's very debated on this test, but
babies are self-aware.
What happened? Wait, what'd you say, Jim?
I think human babies definitely are self-aware, but
yeah. So they say that a baby is only self-aware until I think they're 11 months old. I think I told you that last time, John. People got to fact check me on that. But they also argue that babies don't really care when they're like, growing from like 0 to 8 months. They don't really care if there's a mark on their head. They're not really. Like there's that argument, like, how do you know if they care or not? Like, what if they just, don't care about what they look like through the mirror, So, but there's a bunch of arguments on that test. But I didn't explain the ingredients that were in this mRNA, which I was supposed to.
We went on this entire like 10-minute tangent of like, okay, do caterpillars, do they know they're going to become butterflies?
I kind of want to go back to that after this. We'll see.
All right, fair enough.
Okay,
fair enough.
So
we'll save it.
Yeah. Okay, so the ingredients in this mRNA vaccination, for those of you that are interested in learning, is they're very simple ingredients. To me, like, I guess in biology, like, you hear these are things found in your kitchen, kind of. So we'll see. So you guys will be the judge of that. So the first one, obviously, okay, is it going to be found in your kitchen? It's the mRNA, which is the. Imagine just having.
There's probably like some PhD out there who's just gonna like knock on your door one day. I'm like, oh, hey, Ryan, I think like one strand of COVID-19 mRNA. Oh, thank you very much. It's like you knock on your neighbor's door for a cup of flour.
Yeah. Can I borrow that half mRNA strand, about 2 teaspoons of that strand, please? Thank you very much.
Let me get some guanine and cytosine. Let me get some of those base pairs just in case.
And okay, so and this mRNA obviously is important. Again, it helps create that protein, and so the exact gene sequence that is said to be used isn't publicly available. So they said they're going to tweak it such that, because the virus is always sort of mutating, which is another extraordinary feature of bioviruses, is their ability to adapt and to mutate. But yeah, so the next ingredient is definitely not going to be found in your kitchen. So the other ones are, though, I promise. Fake news. Fake. Just kidding. Okay. It's the lipids. And so in the Pfizer vaccine, they use lipid nanoparticles to encase this mRNA. And nanoparticles are basically a tiny greasy sphere.
Literally, you can literally call it greasy too, because lipids are kind of like the
oil,
the core component of oils, fats.
Yep.
Yeah.
And so they protect the mRNA and help it slide. It slides inside the cells. That's what I put. So it's able to sort of sneak past the barrier, the membrane, and to go straight through. And so the size of this is around 100 nanometers across. So this is nano sized, very small. Christian. Oh man, I don't want to. Do you want to say the last name, John? Because I think I'm gonna butcher it.
Christian, if I get it wrong, do tell us. But yeah, I'm pretty confident it's Schneider.
Okay. Thank you for the follow. Thank you for the support, Christian. Much appreciated.
Yeah, thank you so much.
Thank you for stopping by. Yeah. So, and so it's 100 nanometers across, and there's 4 different lipids that they used. One primary ingredient is the ALC0315. Now, I don't know how they come up with these names, but it sounds like a robot. And so this.
You remember when I had all those astronomy articles? I was talking about how Hayabusa 2 was getting off that asteroid. What was the name? It was Ryugu, but it was like Ryugu something 90. The naming schemes, some of these things are ridiculous. They're absolutely nuts.
Yeah, it's like, why did you choose 0315? Is that someone's phone number? They just slapped onto the end of that? But so what's so special about this one is that it's ionizable. So the RNA is positively charged, so this becomes negatively charged, and this allows the RNA and the lipid to stick together. So that's sort of like the sandwich, keeps it nice and tucked. And the other lipids, one which is fairly common is the molecule cholesterol. And now I remember this in AP Bio, cholesterol is on that lipid membrane that sort of acts as it keeps the structural integrity of the cell. That I know. And also helps stops clumping. So yeah, so shout out the cholesterol. Oh wow, Whale Crazy Official. Thank you guys for the follow. I can't really tell unless it says wait tin ho. Thank you guys for the follow. Appreciate the support. And so we gone over mRNA, the lipids, now the salts. So it's the salt is they contains 4 salts, which is wow, I almost went like 4 salts, but anyways, one which is an ordinary table salt, and together they keep the pH of the vaccine close to a person's body. So salt is super helpful in keeping that pH, I guess, within our body to help regulate that level, which is very important because in bio, pH, if you're off by a slight number, that's going to mess up your
body's going to go nuts. But also,
right.
For those in chat who may not be as chemistry inclined, when we say salt, we don't necessarily mean table salt. Like there's a whole umbrella of compounds that consist of a metal and it's like a halogen, a metal and a halogen, or no, it's an alkali. It's now I'm okay. Because I took chem for years, dude. Like I'm really blanking on what a salt is, but it combines two classes of compounds, and it's an umbrella term. So when we say salt, there's more kinds of salts than just table salt. Is what I mean to say.
Yes, sir. Yeah.
So we're not. This vaccine does not contain. Well, I don't think it contains a bunch of table salt.
From the MIT technology, this article, it said which is ordinary table salt, which is pretty interesting.
Oh wow!
So
okay.
it does use like ordinary table salt, which you can find in your kitchen. Hey, let's go. That's the first one out of the list that I said that they're all going to be from your kitchen.
mRNA, which nobody, I don't think, like keeps in their like.
Yeah.
You can't just buy a jar of mRNA. And
yeah.
then, what was the other one? Lipids.
Lipids.
Wait, no, you have lipids in your kitchen though.
Yeah. So I guess I'm right
oils,
on that.
Soap, soap. Like a bar of soap. Usually like when they say like you can make soap out of animal fat, you're just repurposing those lipids because the hydrophobic nature makes them great for getting grime off your hands and other surfaces.
Right, and the triglyceride fatty tails. That's what I remember.
Yeah, this long hydrocarbon chain.
Right.
It's got like this tail, and all our cells, right? It's a lipid bilayer, so it's like 2 layers of these lipids. But so I think when you said salt, I think salt is the second ingredient that we can find in a kitchen.
Yes, sir.
Salt and lipids.
Yep. And so the fourth ingredient is sugar. Wait, is this the third one? No, this is the fourth one, right?
Right, but it's the third one
yeah.
that you can find in your kitchen.
Yeah,
so
yeah.
Kind of staggered by one.
So it's sugar, plain old sugar. In this case, it's sucrose, and it allows the nanoparticles from sticking together and safeguarding them for when they are frozen. Because in this mRNA vaccination, it's really important that when they store it, it's stored at negative 100 degrees Fahrenheit or negative 73 degrees Celsius. So it has to be like pretty cold,
The logistics for this vaccine are like incredibly impressive. Like to be able to ship this stuff. I think I was reading from BBC News. Like you have these specialized refrigeration units that have to go on planes, and then once that refrigeration unit gets opened, you got to get that vaccine out like as soon as possible, because every time you like open and close that fridge door, the temperature fluctuates and the vaccine kind of already begins to lose its effectiveness. So, but the logistics are very impressive on a huge scale. Yeah. And
so the last thing non-ingredient, because there's that I wanted to hit, was that there's no preservatives. And what makes this different from other traditional vaccines is that, but there are no preservatives, which basically means that it doesn't. Oh, here's the thing that other traditional vaccines contain is called thimerosal. Yeah, like thimerosal. I'm butchering it.
I mean, you have the link. You might want to drop it in chat. Maybe the audience can take a look.
For sure. But all the ingredients that goes into mRNA the mRNA vaccine, which is pretty it sounds simple, right? I mean, from a biology standpoint,
Wait, so let's recap. So we got mRNA. Right? We got
mRNA. Yep.
A pinch of mRNA. We got some lipids.
About to go
right?
Gordon Ramsay on us.
We got lipids. We got salts, right? And then we got what else? Sugars, right?
Sugars, yep.
And then you said no preservatives.
No preservatives. Yep.
So I don't know. So we laughed our butts off at this one, but nobody keeps like a jar of mRNA sitting around in their kitchen. So that leaves you 3 ingredients. That's where lipids. So you can find those in oils, animal fats, and then you have your sugars, and then you also have your salts. Wow. So I guess the stuff you put in your body. I mean that sounds pretty darn safe to me. That sounds pretty darn safe.
Right, and this goes sort of in the context of okay, well, what am I putting what does this new vaccine have? Right, the ingredients people are scared of, but it breaks it down really nicely to the general public of what's in these vaccinations. And I didn't know I didn't know these ingredients. I thought vaccines were pretty complicated, that it needed like these certain chemicals, like these certain I don't know,
like
these chemical terms. Right. This sounds safer than eating, I don't know, some foods in your everyday store. When you flip that back, you see the active ingredients or the ingredients of some food.
It's scary.
Some
of that stuff is scary.
Right. Yeah. So I mean, this mRNA vaccination, I would say I would give it the 2 thumbs up, and I think,
Is that our next podcast idea? Like today we're gonna rate vaccines.
Yeah.
Overall, I give this vaccine a 2 out of 5.
Let me give a little taste test. Does the mRNA taste good?
Now I'm imagining out of humor, how IGN and there are all these outlets that review video games. Like, today we're going to review this medication. So we've looked at the statistical results from this. I mean, statistics is incredibly important for the medical field because you're dealing with live test subjects. You got to like your probability like p less than like it's like a threshold or something.
Right.
A ANOVA or chi-squared test. And I'm just imagining, like, thanks for tuning in to Medical IGN. Today we're going to talk about how this vaccine or this test got like a chi-squared better than.
Yeah, no.
I mean, just we're both engineers. We geek out about different. There's bound to be other scientists that geek out about like saying like, whoa, we found a particle with a massive, 21 giga-electron volts that we've never seen before.
Whoa, dude. Poggers. Pog in the chat. Pog.
Pog.
Imagine if like the science world met Twitch.
I mean, I looked up, I went on Google Images once and I looked up Pog, just because like I just wanted to see what came up. And some ESL, is it ESL? English second language, or is it ASL? No, that's American Sign. It's definitely ESL. Like people who learn English as a second language, there are websites that help you, learn, and they cute graphics and resources. And they're starting to add internet colloquialisms to those websites. And I saw Pog as one of them, and a bunch of other like Twitch-related terms. So just imagine like you're from a foreign nation and you're learning English, and like near the end of the curriculum, Twitch terminology. So, and I had a friend of mine. I was telling him like before my job interview, I was worried like, bro, I better not say poggers like in the middle of a job interview. They're like, this algorithm runs an O of n log n time. That's pretty poggers. And I'm like,
oh my god.
I really hope I don't say something.
I hope not, John. That would be interesting.
I mean, once finals are over, I mean, we still got next Sunday. We still, we're still keeping the heat on. We got some great articles.
Oh yeah.
I mean, science. We might have to hunker down, but the field of science and technology never rests.
Always progresses. Yes, sir.
Yeah. We greatly appreciate once again our new followers, and we look forward to next Sunday when we'll have another round of the 0x2C podcast.
And for anyone that's new that joined in today, again, like John said, appreciate the support, and we'll be back here next Sunday. Yeah. All right, guys. Have a good night. Bye.
Bye.